Good evening and welcome to the Solstice Star Party. And Calvin, if you can.
Yeah, so first I'd like to acknowledge that we're on the traditional territories of the Coast Salish and Lekwungen speaking peoples who are custodians of these lands and waters. The area that we're broadcasting from has been the gathering places of the Songhees, Esquimalt, and Hasanich people long before the arrival of peoples from other places, and that continues to this day. So also the Dominion Astrophysical Observatory in the center of the universe building, which we are not presently on because this is a virtual star party, are on the ancient hill known in Senchothan as Hitikis. So we appreciate the opportunities to work and learn on these lands, or virtually.
Thanks, Calvin.
Yeah, no problem.
If you're on Zoom, you can type questions into the chat window. And if you're joining on YouTube, you can also use the chat feature. And tonight there will be an astronomer segment. And so save your questions for that time, or questions for the speaker will be saved for the end of their presentations. We've had a wonderful year. The Friends of the DAO picked up steam with the popular summer weekday tours for the center of the universe and in-person tours, and of course, our education community tours. We are looking forward to your help for raising $12,000 to continue our school tour program. And your donation of $100 will cover the costs of 50 students participating in a school tour. We introduced 4,304 children in 89 school sessions to the fascinating world of astronomy and related innovative engineering since December 2021. And fall 2022 was our best yet, with 28 school visits, up from 14 in 2021. And even with the recent hill closures, we have been able to pivot and continue with both virtual and classroom visits. If you feel like this is something you'd be able to contribute towards, you can visit our donate page on the website at centeroftheuniverse.org. We sincerely appreciate your support.
Yeah,
Tonight's star party.
Chat.
Sorry?
I'm going to put the link to our donation page in the chat.
That's perfect. Thanks. Tonight's star party will feature the ever popular What's Up in the Sky segment. If you have a space-related question, please ask during the Ask an Astronomer segment. We will have the second installment of the virtual dome tour, behind the scenes dome tour, electrically assisted astronomy group talking about imaging Mars during the occultation, and a little bit. And our speaker tonight is Nathan Hellner-Mestelman, who will be speaking to us about the largely unexplored distant future of the universe. We hope you enjoy tonight's star party, and we look forward to welcoming you back to the next one on January 28th. So Dawn, can you kick off the What's Up in the Sky segment?
Sure. Well, welcome to What's Up for the Sky for December 17th, 2022. And we're going to start off with what's up in the gift shop with Stephanie, one of our board members. And we'll just start that in a second, but just to say that with the holidays coming, and if you're interested in buying something for somebody or for yourself for Christmas, don't be discouraged because the hill is closed. The gift shop is still open virtually, and so we can either mail or bring your order to you. So obviously, with time drawing down before the big day, it's probably best to bring it to you if we can. And so I'd also like to make a plug for, and I'll do this later as well, for taking out a membership in the RASC. It makes a great gift. And so with that, I'm just going to pass it over to Stephanie to talk a little bit more about the gift shop.
Thank you, Dawn. Just going to share a few slides with everyone about the gift shop. So we all know, as Dawn said, it's the time of the festive season and sort of the gift-giving season in a way. So what better way than to get something from the Friends of the DAO to give to your friends and family for Christmas. So we have a lot of stuff in the gift shop. This is what our gift shop looks in real life when you get to come up again, and we love to have you all there. But we want to focus today on our celestial buddies, which is probably one of our best-selling items. It's plush animals with different planets, and everyone loves them. It's very popular with the children. And so we just thought if you would like to have one, this would be a great gift for any child, young to old. We always have to restock because they're just so popular. We also have a new astronaut buddy and a Polaris buddy, which actually light up. So that's even better. Plus, of course, we currently also have the Mars buddy in stock, which will feature the big part of the EA talk later today. We also have a lot of books, especially on Mars, as you can see, in English and in French. And we also have multiple of Bob McDonald's books for you to order too. We also have a lot of products from local makers and vendors. So we like to support local people since we're a local group too. So don't hesitate to buy anything from them too. We have our gift shop is online, and so you can order 24/7, 7 days, 24/7, and just explore whatever you wish. We also have like the mini Galileo telescope, so another great gift. It's only $25. The celestial buddies are around $30 to $40. Yeah, and just scroll through. There's a lot to see. I will put the link in further after I finish my talk here. But yeah, just check it out. Never hurts. And all orders need to be made before December 22nd, by December 22nd. If you would like to receive it latest on December 24th, any order made after December 22nd will unfortunately have to, will only be delivered to you by after January 5th and not between Christmas and New Year's. So if you would like to have a Christmas gift or New Year's gift, best to order as soon as possible, but make sure to order before December 22nd. We have a lot, if you're wanting to donate or don't actually want to give a physical item to someone, we also have memberships that you can buy from us, from adult membership, family memberships, junior astronomer, affinity, and infinity memberships. And this is on our website. You can see the different options that we have. An adult membership is $20, and that's for a full year from when you sign up, and you will receive our newsletter, member-only events, and advance tickets to the star party. So usually they will go out 3-4 days before everyone to the public has access to them. So it's a great way to secure your tickets because usually the members will secure a very great portion from it. So that's what gives you an extra since our star parties are free anyways. The family membership is $25, and you can have 2 adults and up to 3 children. So therefore, a junior astronomer membership is free. You can also purchase an affinity and an infinity memberships, the affinity being $100 and the infinity memberships being $1,000. When you are a member with us, you get 10% off in the gift shop. So if you buy a membership today and or tomorrow and you would like to order something for Christmas, you can get your Christmas gift 10% off. And you can buy all of these memberships online at centeroftheuniverse.org. And so, as I said, these are our perks. And of course, you can vote at the AGM, which usually takes place at the end of October every year. And of course, get into our Zoom star party instead of the YouTube version. So yeah, that's all I have from the gift shop today. If you have any more questions, I will put the link, as I said, into the Zoom link and on YouTube, so you are free to go and order right away, or of course, continue listen first to the rest of the star party.
Okay, thank you, Stephanie. And those are great slides. I think Amy did those up. Is that correct?
Yeah, so thank you to Amy. I am just using her slides.
Yeah, but those are great. So thank you to both.
And I hope, yes, thank you very much. I tried to do justice.
Okay, so on with what's up in the sky now, and just to start with the basics here. So sunrise was at 8:01 a.m. today here in Victoria, with astronomical twilight starting at 6:05 a.m. So it's dark until quite late in the morning now. Sunset was at 4:19 p.m. and astronomical twilight ended at 6:14 p.m. And so we've just come out of the week of earliest sunset, which was at 4:18 p.m. So it kind of stays at that for about a week. And sunrises will get later until about New Year's Day. So as we've said before, both earliest sunset and latest sunrise are offset from the solstice because of the ellipticity of the Earth's orbit. And the next week or so is the next month is really your last chance to see the summer stars, given our motion around the sun and the fact that the sunsets are starting to get later. And you'll see a rapid change now in which constellations are visible in the western sky at sunset. And this also means that Saturn will be further down each night and soon won't be visible. So if you're getting or giving a telescope for Christmas, make sure that you have a look before essentially the next few weeks are out. I'm just going to now just see if I can share my screen for Stellarium. And hopefully we can see this. This is the current time. And you can see that Saturn is now slipping down there in the southwest. But you can actually see still, even at this time of night, you can see some of the summer constellations. You can see the summer triangle, for example, over there, assuming it's not cloudy. Okay. So as time goes on, of course, Orion is going to take on more prominence. It's currently over in the, I think it's the south-southeast, and it's coming up, and it'll be much more prominent in January. And the Orion Nebula, which is down here, is down in the Sword, is an excellent target for small telescopes. And the Andromeda Galaxy, which we talked about last month, is pretty much right overhead and still very, very well placed. And of course, to see that with your eye, you need to get away from light pollution as much as possible. And so as usual, for more information on sunset and sunrise times, Time and Date is a really excellent source. So the moon phase right now is a waning crescent in the morning sky, with the new moon arriving just 2 days before Christmas. And that means that people with a new telescope will have a fantastic target in the evening sky, in addition to Jupiter and Saturn. And Venus is not currently visible in the evening sky, but will emerge next month as a literal bright spot to begin 2023. And currently, Mars is visible all night long and was at opposition this month, which we'll hear more about later, which I'm excited to hear about. And as we heard, was occulted by the moon, or in other words, eclipsed by the moon. And so you'll see some great images of that as part of the talk as well. And also if, there's plenty of really great images online. So Mars is about twice the diameter of our moon, but it's also 200 times the distance, meaning that it's about 100th the angular size. So you can work out the geometry for that if you're bored. Last month I talked about comparing the colors of Betelgeuse, Aldebaran, and Mars. And here you can see them over here. There's bright Mars up here, Aldebaran and Betelgeuse. And I actually did that while watching the Geminid meteor shower. And so it was kind of interesting to really do it. And I found that Mars's color was noticeably different from both Aldebaran and Betelgeuse. And it's also arguably a lot more colorful, just plain more colorful. And well, why is that? A lot of it has to do with the fact that Mars is a lot brighter than those other two stars. While they're very bright stars, Mars is significantly brighter. And your eye simply responds better in terms of color to brighter things. And so to sort of minimize that effect a little bit, what you can do is take a pair of binoculars and then check out all three and see if it enhances the colors a little bit more of Aldebaran and Betelgeuse. And to just dial it up a notch even further, what you can do is put your binoculars or small telescope just out of focus, and you'll find that you can see the colors more distinctly as well. So that's a nice little visual observing project for you. So clearly over here, we can see that Jupiter is very well placed in the south, and obviously a great target with small telescopes or even binoculars for looking at the moons and so on, the Galilean moons. And it sets at about 12:24 a.m. tonight. And Saturn sets at 8:52, But to get a good look at the rings, you'll want to try to capture it just after twilight or late twilight if you can, because it's getting very low in the sky. And so as at 5:45 tonight, it was only 22 degrees off the horizon. So that puts it at about 2.5 times the thickness of atmosphere that we're looking through compared to looking straight up overhead. And so that's also going to be 2.5 times the air turbulence as well, which is going to blur your view. So as it sinks lower in the evening, your view is going to get worse and worse, as I think a lot of you already know. So I think what I'm going to do now is just talk a little bit about the sky events in the coming year. There's lots of exciting things to talk about. And so let's just move ahead here and look at the 23rd of January. And so we'll actually, and I think I'm going to have to look a little, oops, I always have to make at least one little flub here, technically in my presentation, right? So usually more than that. So over here, and I'm just going to advance the time so it's a little bit darker, but you can see that Venus and Saturn will be close together in the deep twilight. And so you might not see a lot of detail with either one because they'll be down so low, but at least you'll be able to see them together and they should make quite a nice pair. And so why won't you see much detail at that point? Well, as I said, it's very low, and on that, at that time, you're going to be looking through about 8 times as much atmosphere as when looking straight up. So, you know, just be something to see them at all at that time. So let's skip ahead here to about a month from then, February 22nd, and then you'll see on the 22nd, you'll see the moon and Jupiter quite close together, and I don't think it's quite visible here. That's okay. And brilliant Venus will actually provide a little bit of it'll try to steal the show a little bit. I'm going to see if I can zoom in a little bit on this. Maybe not. Well, it's not quite showing there. That's all right. And on March 1st, let's just back off the time a little bit. And make it a little darker. Okay, and I'm going to try to zoom in. You're going to see Venus and Jupiter close together. So that's a really spectacular one. And that's one definitely to mark on your calendars. So March 1st. And let's just skip ahead a little bit further here. So on April 11th, okay, and obviously sunset's getting later, so I have to adjust this as well, and I'm just going to zoom out a bit this time and make it a little bit earlier in the evening. Okay. So on April 11th, Venus will be close to the Pleiades star cluster, and that's going to be a great photo op. And on April 20th, there will be a hybrid solar eclipse. So it'll be briefly total in some places, but annular in others, but unfortunately not visible here at all. So you'll be in luck if you're in Papua New Guinea at that point, if you just happen to be there. And this is a time when the angular size of the moon almost exactly matches that of the sun. So it really depends on the arc of the Earth as to whether you see it as an annular eclipse or whether you're just that much closer to the moon and you see it as a total eclipse. Okay, so let's just skip ahead a little bit further here. And on May 22nd, the Venus, the moon, and Mars will be in a line. So see if I can skip ahead here. Okay, and I'll just try to make it a little bit darker here, a little bit further in the evening. Maybe a little bit there. There we go. And that makes sense because they're all essentially on the same plane, although the moon is can be about as 5 degrees north of the ecliptic, and so it's not quite a great line there, but it's pretty good. And on June the 2nd, which I won't show here, Mars will actually move through the Beehive cluster, and that'll be a spectacular sight in binoculars or a small telescope. So again, a great photo op for that. And just a note here too that the moon phases will be excellent for the April Lyrids and the August Perseids, as well as the December Geminids. And so it's another terrific year for meteor showers. And so let's hope that clear weather holds for all three. But I think the highlight for this year, this coming year, is going to be the annular eclipse, which will be visible from nearby Oregon and an arc down through the U.S. and I believe parts of Mexico. And so let us know if you plan to go down there. We may join you. And I was going to say, just a little plug here, there's many excellent sources for these sky events that I draw upon for these talks, but you really can't do any better. Here's a little sales pitch for the RASC. You can't do any better than this, which is a publication of the Royal Astronomical Society of Canada. And it's just one of the many benefits of joining the RASC. And it actually astounds me how they put this thing together every year. It's over 300 pages, and it's just absolutely jammed with detail. Our own board member, Laurie Roche, contributes several pages to it, and it's just a fantastic benefit of membership beyond all the other benefits of being a member of the Royal Astronomical Society of Canada. And I'd just like to conclude with one little thing, which is, I guess, a little bit of a celebration here. Saanich was named as one of the 14 bird-friendly cities in Canada by the COP15 Biodiversity Conference in Montreal. And a large part of that has to do with the fact that Saanich actively tries to manage light pollution, which helps make it bird-friendly. So that's one of the key criteria for being a bird-friendly city. So well done, Saanich. Thank you so much. And you're also making astronomers happy at the same time. So that's it for me for this week, and Happy New Year to everybody.
All right, thanks, Don.
Okay.
Yeah, okay, great, thanks. All right, so I'm going to do the second part of a virtual tour to sort of, in the spirit of a star party where there would normally be several tours of the dome, I'll at least do a virtual tour. So here is the Dominion Astrophysical Observatory. There it is there. So this is the big white building with the dome on top. Those of you that drive around Saanich and Victoria may see a big hill with a white building on it, and that is this one. So I can go inside. And if we look on the floor, we can see here it's got some writing on it. It says DAO, that is the name of the building, Dominion Astrophysical Observatory. And it also has the year that the building was built, 1916. So this building is over 100 years old. And at the middle of the building is this large cement pillar that goes all the way up to the second floor. This is called the pier, and it is basically the foundation for the telescope. So the telescope sits on the second floor on top, and this keeps it very steady. And we go up these stairs to go see the telescope. So coming up through the floor is the pier, the cement foundation that's painted blue here. And then on top of it is this yellow part. That's the mount for the telescope. And that lets the telescope rotate around and point in different directions. You can even see there's an electric motor here on this big gear that lets it rotate around. And this is the Plaskett telescope itself. It's just pointing straight up here. And up at the ceiling, this is the dome, and these are the shutter doors that are right here. So these shutter doors can open at night so the telescope can see through, and also there are wheels all around the dome, so the whole dome top part can rotate around so that opening can point in any direction, and the telescope can also point in any direction and look outside. So what I can do is I can show a video. I think I actually have to stop sharing my screen for a second and then redo this. And I'll just show an animation, or not an animation, a recorded video of the dome opening up here. This was recorded during the daytime, so that's sunlight shining through. And these shutter doors, when they open, they are rather creaky and loud. And this extra cover here will also slide back. And the whole dome can rotate around. It rumbles around on all those wheels. And the shutter door and these wheels are loud in contrast to the telescope itself, which in a second we'll see rotating. And it will it actually moves rather smoothly and quietly, because that's the actual precise part of the telescope, is the actual mount. So we'll just skip this ahead as the whole dome rotates around. And this is a bit sped up, but you can see the electric motor there going around and the telescope moving. Okay, and now I'll go back to the other photographs here. So the telescope in this picture is just pointing straight up. And I mentioned I showed in the previous virtual tour the mirror that used to be inside this telescope. So that sits at the bottom of the tube here. And so that focuses all of the light. It's 1.8 meters in diameter. And when it's looking at a star, it collects all that light and reflects it back all the way up to a secondary mirror, which then reflects it again and focuses the light all the way down through the hole in the mirror, right down to the bottom into this instrument here. And this is basically has a digital camera inside that takes a picture. But what happens is this is actually a spectrograph in here. So it actually takes the starlight and then it goes through a diffraction grating, which spreads the light out into a whole rainbow of colors. And then the digital camera takes a picture of those colors. So that's what this instrument on the telescope is designed to do, because you can learn a lot about stars and other things in outer space by the colors. You can learn about what they're made out of and some other things like how fast they're moving. There's another way that this telescope can be used. I mentioned that there was a secondary mirror up here. There's a mirror, they can replace that with another mirror that actually reflects the light sideways into a digital camera on the side. And that is a camera designed just for directly imaging things without the spectroscope in the way. So that way it takes pictures that you might be more familiar with. And we might actually see some photographs that this telescope was taken for the EAA. I actually can't remember if that was confirmed that we're going to see that or not, but that can be something that we look forward to. And I think that's about it, but I think I'll take this quick second here to enter into this room over here, which is the control room. So this is how the telescope is used, is all the moving of the telescope and the dome. It's all done on a computer. And so on the computer, the astronomer would give the commands to point the telescope in a specific location, and then it would they would take the images and store the images digitally. Of course, over 100 years ago, that was not the case.
Wild lands and waters, meaning less pressure on the creatures that live there.
All right, so I'm going to
But an awful lot
pretty much
has
end it
changed
there.
since the
Maybe I
first
can click over
Europeans
here just to
arrived.
show the telescope from a bit of a different angle. but-
Historically, the great forests of Cuba were cleared. Essentially, any forest that could be easily accessed in the lowlands were all cleared for things like sugarcane plantations, for gathering charcoal, for timber, for
Right.
building, and all that sort of thing.
Oh, I can't do
And I think
that.
sometimes people would come to a
Controls
place
from
like
here.
this and they
All right,
think,
so I'm
oh,
gonna
it's all
stop my
lovely and
share.
green, but it's a very different green than it should be.
And I'm just going to. All right.
The reality is that Cuba's natural world is a shadow of what it once was.
Yeah, I'm not really sure where the
And
audio is coming
the
from.
amount of the damage was due to a system that bedeviled this part of.
There we go. Okay, thank you. All right. So that's about all I had for the for showing off the telescope. So that can be found on our website as well, that virtual tour. It was pretty brilliant. It was made by Aaron Bannister, and they made this whole photographs in 360-degree views. That's like pretty much a program that's typically used for like real estate to show off houses, but it was perfect for being able to show off our own telescope without people having to actually travel to the top. All right, so I believe we have our Ask an Astronomer coming up. Who do we
Calvin.
have? Oh, Evan.
I believe I will introduce this. So let me know when you're ready.
I believe I'm ready. So I didn't have I didn't go through a whole lot for that virtual tour because I did lots of it in the previous one. So we can move right on ahead to Ask an Astronomer if there are any questions. I'm not sure if there are, but it's you, Evan, and is that
and Sarah's here.
And Sarah.
So I can introduce her if you'd like.
Sure thing,
so,
yeah.
First of all, hi, I'm Evan. I've been a volunteer at the center over the last year. Now is your chance to ask any questions you have about space. So please type the questions that you have into the chat window, either in Zoom or YouTube. And this Ask an Astronomer panelist today is one of the SDAO board members, Sarah Al-Shamali. I hope I pronounced that right. I'm so sorry, Sarah. So Sarah graduated from the University of Victoria with a BSc degree in physics and astronomy in May of this year. So she is currently doing research for the UVic Atlas group, where her main task is to optimize event selection of rare B meson decays to electrons in the Atlas detector at the LHC. So Sarah is planning on pursuing graduate studies in either experimental particle physics or observational cosmology, studying the phenomena of dark matter or dark energy. She is fascinated by these phenomena due to the fact that they constitute a big part of our universe, but are still mysterious to us. Being born in Iraq and growing up in the UAE, Sarah has always wanted to make science more accessible for youth. So she currently runs her own space page on social media platforms in both Arabic and English to engage with the public of all ages and backgrounds. I can attest to this. I follow this account. Very good. Communicate science and help inspire Middle Eastern youth to venture into the STEM field more. So here we go, Sarah. I hope you're ready. I can't see you here right now, but
don't have her video up yet, so I can't bring her on. Oh, wait, there we go. All right.
Perfect. Right.
I hope everyone can hear me okay. I'm in a cab. Letting you know.
Can't quite hear you there.
Is spotty.
Can everyone hear me okay?
Yeah, it's not working so well.
Quite laggy, yeah.
Yeah. while we see if you can we can figure that part out, Evan, we don't have a whole lot of questions up yet. I did want to ask or have you have somebody explain, because Dawn did mention that there was an annular eclipse, and so I'm wondering if maybe you could talk a bit about that.
I don't know if I know enough, honestly, to talk about this.
Oh, okay.
So I'm sorry, but yeah. Do we have anyone else around here who's?
Well, if Don wants to spend more time talking about it, he's welcome to.
Okay. Oh, I see, Laurie.
Sure, I'm still here.
Sure, yeah, I'll bring you on just to explain it a bit more.
Sure, I'll put my camera on in a second here, but basically the moon varies in distance between the where we're, that's just I guess a way to summarize it. It varies in distance to us because it's in an elliptical orbit, and so whether the moon appears to be smaller than the angular size of the sun or larger depends on where it is in its orbit. And also there's also another factor too, in that we can be at a different distance from the sun. So the angular size of the sun also varies as well. So how those two things combine will determine whether you have an annular eclipse or a total eclipse or something like this, which is both. And so that's basically what's going on. So I mentioned that basically if you were closer to the moon while this event is going on, then that will actually help determine whether you see it as total or annular. But it's also just your position on the Earth. So it's simply your distance from the moon on the surface of the Earth as to whether you're going to see it in that particular phase. And the alignment as well also makes a difference, like whether you're right in that line or off to the side or not, as to whether you'll see any eclipse at all. So hopefully that made a little bit of sense.
Yeah, thanks, Don.
Okay.
Yeah, it's that interesting thing where it actually becomes important that the moon isn't a perfectly circular orbit. A lot of the time you get used to saying like, hey, you can just approximate it to a circle, but it actually matters in some cases.
Yeah, that's right. So the alignment is right in terms it's on that, it's everything's in a line, but the distance is just almost exactly matching the angular size of the sun. So it is a fairly rare event. It's usually one or the other, but yeah. And Dan Posey said, we can thank Kepler for this knowledge. I didn't know that. Thank you, Dan. Feel free to speak up on that if you want to.
About elliptical orbits and the varying distance of bodies from whichever planet or the sun that they're moving around. Not so much about the annular eclipses. I think that was probably an input into devising the laws, but I'm not sure about that one.
Okay, I thought he actually was specific. He meant to say he specifically talked about hybrid eclipses or something, but okay. So yeah, of course, the notion of elliptical orbits versus everything being perfectly circular. And of course, I think he wanted, as the story goes, he wanted things to be perfect geometrical figures. Not that I would think of an ellipse as being imperfect, but he thought that a circle would be more perfect. And so it was a slightly disturbing finding, but being the great scientist that he was, he had to conclude, based on the observations from Brahe and others, that in fact objects do move in ellipses. So he gave up his cherished beliefs for the facts. Okay, I guess that's about it. Anybody going to Papua New Guinea for this?
No, but if anybody's curious, it also feeds into king tides. So as we get into January, in that case, it's going to be perigee with the sun that feeds into the slightly stronger tides that you can see, where it's not just the time of year, but I think we're closest to the sun on something like January 4th.
That's right. Yeah, it's counterintuitive, but yes, we are closest to the sun then.
So if you get the moon to line up with the sun for the higher of the high tides at that timing, you get the really extreme king tide effect.
I saw a great photo from the seawall taken by a friend who was running there a few days ago, and the water was almost up at the level of the pathway on the seawall. So it was actually quite impressive. And I wouldn't want to be there in a storm, but yeah. And as many of you know, there were houses damaged close to Gonzales Hill a few years ago when there was a storm right at the time that there was one of these king tides, and just washed right over Dallas Road, and actually I think one of the houses had to be ripped down, as a matter of fact. So after that, so yeah, keep your eyes peeled for that as well.
Hi everyone, I'm sorry. Can anyone hear me okay now?
Yes.
Much better.
Perfect.
Good now.
It's clear now.
Great. I'm so sorry. I was in a cab and the internet connection wasn't stable, so I apologize.
Cool. Okay, I can't see any questions if people are asking them yet, so I don't know if you can. I know. Can I ask you a question?
Of course, go ahead. Yeah, that's what I'm here for.
So, what brought you to study astronomy?
Ooh, that's an awesome question. So, I've always been fascinated with the skies and with the stars and the planets ever since I was a kid. And so I didn't know I can actually study that as like a part of a degree or like part of like a scientific field until I got to high school. And then one of my teachers, he was telling me that, you could actually pursue this as like part of a degree if you would like in when you're studying like bachelor's or whatever. And so I was like, okay, cool. Yeah, of course I would love to do that. I didn't know I could do that even before. So I managed to be interested in astronomy as a field throughout, like ever since I was a kid. But like, it wasn't until I got to high school that I realized I can actually study this as part of a degree.
Cool. Yeah, that was like a story I heard of another astronomer working at the NRC. I think she from Australia. She said there were just like these 5 jobs that people were used to hearing about, doctor, lawyer, teacher, whatever.
Yeah.
She didn't realize she could actually go and study like astronomy, something so cool.
Yeah, exactly. That was exactly my spot too. I didn't even realize that was an option for me at the time. So I was like, okay, cool. Yeah, I guess I'm going to study astronomy now. So it was pretty awesome.
Yeah. Cool. I still don't see any more questions. So could you describe the ATLAS project and what you're doing in that realm?
Yeah, of course. So ATLAS is an experiment, it's a particle physics experiment where it's part of a larger project where it's just a particle collider. So that means they bring 2 particles, protons, and they collide them at very high energies. And they study all the different kind of stuff that come out of these collisions. And so my specific task is to analyze the data points that come from studying beam meson decays. And so basically I try to, it's called trigger development. So I try to optimize how good the ATLAS detector itself can pick out good data points given that specific rare beam meson decay. And apparently it doesn't do that job very well because the particles that come out of that decay are very low. They have low momentum, and so they have fairly lower energies than the other types of decays that are studied in the ATLAS detector. And so I had to come up with ways on how I can implement changes to the collisions or to the triggers themselves so that we can pick out the good data points from there.
Cool. Was that like a project that you did through UVic?
Yeah, so I contacted a faculty professor at University of Victoria, and she did tell me that she had a spot available. And I've always wanted to do particle physics because I always thought it was so cool. And so I finally got the chance to actually work in research in that field. So it was a huge learning curve for me, but it was amazing.
Cool.
Yeah.
Lori, if you want to interject, you were welcome to. I saw that you were waiting.
Hi, everybody. I'm coming in here from Hawaii. I'm sorry.
Hello.
It's an absolutely lovely night, and it's gorgeous here. However, Sarah, I wanted to know from you, how can organizations like the Friends of the DAO and the Royal Astronomical Society use the resources and use the people that are at UVic better than I mean, I know that we try and we try to get connections, but is there some way that the students that we don't know enough about what the student schedules are, or how we can kind of do that better for the students so that we can involve them a lot more and because I mean, it's just an untapped, I mean, amazing resource there for everybody, and we'd love to be able to have more, but we want to be able to not overtax anybody specifically, or do something that's not that won't work for you guys, right? Like, we need to kind of do it both. So I'm just kind of putting you on the spot a little bit, but
yeah, no, that's an amazing question. I think a lot of students like myself, and even first and second year students, they would love to have the opportunity to be involved with Friends of the DAO and just help out with the observatory in more ways than one. I think that the best way would be for one of the people working there, like such as yourself or someone else, to reach out to the Department of Physics and Astronomy at UVic, and tell them that you would love to involve the students more, because I do believe that there's a lot of students who are very, very interested in that kind of thing. And I know for myself that like, if I didn't have, if I couldn't talk to Karun or to any of the people that were volunteering for the open house at UVic, I wouldn't have known about the different possibilities that I could be involved with the DAO. And so I think that if one of you guys would just reach out to the department itself and just tell them that, hey, we would love to involve the students more, like, I mean, maybe they can tell you which ones are interested, or the different, like, maybe there's like a voting poll that can be done so that we can see which ones would have availability based on their schedules and classes and whatnot. So I think the first way would be maybe to reach out to the department, and I mean, I can help out with that as well, like, if you would like any help. But yeah, I am sure there's a lot of students who would be very interested in helping out. You're welcome.
And not just university students too, high school students.
High school students, yeah, exactly. Exactly, yeah.
Yeah, I know several people, even in my grade, who are just as interested in astrophysics and stuff, but they don't really know the opportunities there are, even just in Victoria.
Yeah, for sure.
Yeah. Well, moving on. I have another question. So, sure. What do you think? Is there dark matter in every galaxy?
That's a very loaded question, but I mean, dark matter is everywhere in space. It is more evidence in galaxy clusters, and that's why there are large-scale structures, like studies of large-scale structures in the universe, where you can look at these large galaxies, large clusters of galaxies, and study the distribution of dark matter in those clusters. And there is also the small scale structure, which is basically astronomers studying the dwarf galaxies, because for some reason it is a bit more predictable how galaxy clusters behave compared to dwarf galaxies. And so, I mean, they both have dark matter components in them. And the reason why we know this exists is because of the way that these galaxies are held together. Comparing models to experiments or observations, the cosmological model does show that there is a dark matter component that is supposed to be there, and that's why we know it exists. But however, because it's dark, because it doesn't react with light in any way, shape, or form, it's a bit hard for us to study dark matter directly or indirectly. And so that's why you have different fields coming into play to study dark matter, such as experimental particle physics and particle colliders, or observational cosmology and astronomy and astrophysics, which is to observe galaxies in the sky and just study the distribution of dark matter, the mass, if it is even made up of particles, its properties and how it behaves and that kind of stuff. So I would say there's dark matter everywhere in the universe, but I think it would be most evident in galaxy clusters, because that's where you have, I think, a larger distribution of it.
Cool. I think David Lee has a question.
Yeah.
Yes, thanks, Sarah. Now that you're talking about dark matter, I often wondered, I mean, we see or we observe things by inference often, and just because we don't see something visually or detect something, it doesn't mean it doesn't exist, thus dark matter. Do you think we will ever have a method of detection where we will actually see it?
That is $1 million question. I honestly, I don't know if we will ever actually directly detect dark matter. I mean, I know there are lots of candidates for potential particles that could make up dark matter. And again, these are done through studies of like experiments like the Snow Lab experiment in Canada, and Alice as well, and Bell and stuff like that. It's very hard to say. I mean, personally, I think we would not, I don't think we would detect dark matter directly within the next, maybe, I don't know, 10, 20 years. However, I think we can predict some of its properties through observations of the night sky or of the universe. And I think like once we do that step, once we do realize like, okay, some of its properties are so and so and so, we can then rule out some things that we didn't know before, and then focus on other things that might bring us closer to figuring out what dark matter really is. I think, like I said, the standard model in physics is a very great theory, but it is incomplete. I mean, there are still things that we don't really know what they're made up of, like dark matter. And I mean, just not too long ago, we just discovered the Higgs boson, and so that was added to the standard model. And so that just tells you that things we already know or that we already thought were complete are actually incomplete. And so that just adds a whole other dimension of possibilities and theories and hypotheses that we just didn't know before. So
yeah, I often wonder whether modern day astronomy is taking maybe a different stance in terms of what we don't know, because I think if you think historically about astronomy, people were purporting what they thought they knew. I don't know if they even thought that they wouldn't know. They just said it's like this.
Yeah.
And yet we maybe a little bit more humble and think, no, we don't know that.
Yeah, for sure. I mean, with newer technology and telescopes like the James Webb, that will obviously bring us closer to figure out what's going on, just because we are able to have more accurate simulations, and thus comparing our observations with simulations, and then always coming up consistently with ways to how we can improve both sides. And so that will bring us closer to figure out, things like dark matter. But I think we are still, because it's just because there are things there are tremendous things that we don't even know what we're looking for, like whether it's in particle physics or astronomy. And so that would just increase the possibilities of what to look for in science. Yeah.
I guess you won't be out of a job.
No, definitely.
Sarah, can you see yourself doing this for your whole life?
Oh, for sure, 100%. Are you kidding? Nice. Yeah, of course. It's very interesting. Even if we don't know what's going on, it's still very, very interesting. Yeah.
Is that like your dream, sort of to be on that cutting edge of that sort of science that's going on?
Yeah, I've ever since I was in high school, I've always liked cosmology for some reason. I think it's because, like you were saying, that it's just so mysterious to us, and we don't really know like what's going on. It's just this whole like dark thing, right? It's the same thing with black holes as well. We don't really know. I mean, we know more about black holes than we know about dark matter and dark energy, but we still don't really know what a black hole is in specific. And so all of that mystery just definitely adds to the interest of me wanting to like pursue that kind of stuff.
Can I chime in here? It's Don. I said I was going to be quiet and go away, but the great Harvard professor, Dr. Margaret Geller, said back in the 90s in a lecture at UVic that every age has questions it can answer and questions it can't. And sometimes other areas have to catch up in order for us to answer those questions. And I think she talked about, for example, the discovering the expansion of the universe back in Galileo's time. Well, the telescope technology wasn't there. He had just barely invented the telescope, and understanding like spectroscopy had not been invented yet, and things like that. So it might be a while until other areas catch up. But I thought that was such a brilliant comment by her.
Yeah, yeah, of course, 100%. And I think it was also Richard Feynman, who said, if you think you understand like quantum mechanics, then you don't understand quantum mechanics.
Yeah.
Yeah.
Okay, it is about that time to do the speaker presentation. So I'll bring on David Lee to introduce our speaker. Thanks, Evan. Thanks, Sarah. Really appreciate you guys coming on here. It was brilliant.
All right. Thanks for having us.
Yes, thanks.
Yeah, thank you so much. I think it's maybe this episode we should be celebrating youth, because we've got so much kind of new energy out there. So anyways, I'm pleased to introduce Nathan to you. I've got this list of his accomplishments, but I have to admit, the first time I encountered Nathan was actually on TV, because I think maybe Nathan could correct my memory, but I just remember this article of a young boy trying to determine where the planets would be along a street. Was it down in Dallas Road? I can't remember, Cook Street, but I do remember the article. But that's what I remember. So Nathan is 15 years old. He says he's a major astronomy enthusiast in grade 10, and he does public outreach in lots of different ways. He belongs to the same organization that I do, the Royal Astronomical Society of Canada. So he's involved in also a multinational astronomy group that he co-founded called Cosmic Generation. And I think that was just in January of this year, with 4 other youths from across 3 countries. So he's also been published in Sky News, the RASC magazine, and also Skies Up magazine, which is part of the Explore Scientific Initiative. So he seems to be very multi-talented. So maybe possibly he's too young to be a Renaissance man. Maybe he's a Renaissance youth. But he recently produced a film and music series on the immensity of the universe, and it's called Seeing Beyond, and I think that's somewhere out in YouTube land. And he also draws this is what I found really curious, he also draws a cartoon called Nerd Anomaly. So I welcome the whole audience to sort of check those things out. And his goal is to become an ambassador for spaceflight and astronomy. So I'm really looking forward to this presentation. I think he's gonna tell us how big things are, or
more or less you got
how we think things are small, but they're really not.
Things are big. Things are really big, and we are really small.
Well, thank you, Nathan, please.
Yeah, thank you so much. Yeah, thank you to everyone who runs this show. It's great to be here at the last Star Party of 2022. Yeah, it's awesome to be here with all these like-minded astronomy nerds. And to start, I'd like to say, after being interested in astronomy for almost 15 years, and I am 15 years old, and being part of the Royal Astronomical Society for 5 years now, you get this sort of, I don't know what to call it. It's an astronomer's disease, really. It's where everything just suddenly feels incredibly small. And you look up into the sky and you're like, and you stare like that for a very long time. And then after a very long time, you say, what's the meaning to it all? And this presentation, I'm hoping to bring that all a little bit down to earth. it still freaks me out how big the universe is, and hopefully I can like barely put that into comprehension today. So yeah, I'd like to start with a disclaimer for this presentation, which is that you will not be able to understand this presentation. I will not be able to understand this presentation. Nobody will be able to understand this presentation. And it's not necessarily because I'm a bad presenter. It's just because you cannot comprehend the universe. It's so much bigger than the feeble human mind is capable of comprehending. So I'm going to try to go along with my own presentation. And I encourage you to try and do the same, but no hard feelings, because this is literally on the brink of human knowledge, and the universe was not ever meant to be understood by by creatures as humble as we. I don't know if that sounds too philosophical, but anyway. So to summarize, this presentation is a coalition of 3 major fields in astronomy, which is astrobiology, which is the search for life beyond Earth, whether we're alone in the universe or not. Astrophysics, which is searching for patterns and laws in space and the fundamental forces of the universe. And cosmology, which is like borderline astronomy philosophy, which is the search for the universe's future and origin. The people that study this stuff are called theoretical cosmologists, but the people themselves are real. Just wanted to point that out. So yeah, I want to bring every single aspect of astronomy into this one big picture summary. I don't intend to give existential crises to anyone, but let's just say as a waiver, I'm not held responsible for any existential breakdowns resulting from this presentation. So to begin, one of my favorite things to do is to outline how tremendously small we are on the cosmic scale. And I've tried to do this in a number of different ways, and none of them seem to work because I don't think there is any way to comprehend how small we are. But the most effective way that I've done it so far is to put it in units that seem a bit more familiar than abstract lengths like meters, kilometers, and light years. For example, saying that the Earth is 7 million people wide does not necessarily make it any easier to comprehend, but it does put it in more concrete terms. So let's just start with this as a foundation, that the Earth is 7 million people wide. The solar system, out to Neptune's orbit, is 1,200,000 Earths wide. And as you can imagine, you can see where we're going with this. In terms of solar systems, the local stellar neighborhood, which consists of stars in close proximity to the sun, is a little less than 40,000 solar systems wide. In fact, the entire solar system, the furthest reaches of the sun's extent, reaches about a light year, over 1,000 times farther than Neptune is from the sun. So our sun actually has a very powerful embrace on its surroundings. There isn't really any good way to comprehend how unimaginably massive the Milky Way galaxy is, 2,400 local stellar neighborhoods wide. But one of the better comparisons that I like to use is that if the solar system out to Neptune's orbit were the size of a glass marble, the Milky Way galaxy would be the size of Canada. It probably doesn't help put things in perspective very much, because even imagining how big Canada is not that easy. But at least it's like slightly down to earth. Anyway, so the local group of galaxies is around 90 Milky Ways wide. And one of the freaky things that ends up happening at these scales is due to the fact that light travels at a very slow speed. And it does, to be honest. The speed of light is tremendously slow. Our sphere of influence, like in all the millennia that humanity has existed for, our bubble of light has not reached any place in the local group besides the Milky Way galaxy. So we are non-existent to a majority of the universe. I like that astronomers had the audacity to call it the local group of galaxies at Milky Way scales, millions of light years, and it's local. I like it. a lot, because when you go beyond that, the Virgo supercluster, 11 local groups wide, it is still just our local supercluster of galaxies. It is part of the larger Laniakea supercluster, which actually is derived from a Hawaiian word for everything, if I'm not mistaken. But it's not everything, actually. It's only around 0.0000001% of the observable universe, which is 372 times wider. You can do this whole process in reverse if you want to try and figure out exactly how small we are, but I don't think there's any good way to do it, and I hope that somebody figures out how. I just don't think our brains are built for it, though. But I hope that this has given you some sense, some abstract sense of perspective. There's no way I'm able to grasp this, and I don't know if anyone here can. If you can, that is awesome. One of the things that I like to do to maybe help make this a little more clear is the thumb trick with the night sky. It's cloudy where I am. Depending on where you are right now, even if you're not outside, just hold your thumb up. Behind your thumb, the space blocked by your thumb covers around 20 million galaxies, in which cover roughly 96 quintillion stars, 500 quintillion planets, and 3.8 times 10 to the 76 cubic meters of space. I'm not going to begin to talk about how big these numbers are, but from here to the edge of the observable universe, just behind your thumb is quintillions, so billions of trillions of planets with stories as rich as Earth's story. It is too much to comprehend, really. What could be out there? I don't know. There might be life forms with their own forms of hands doing this exact experiment, wondering how big the universe is and trying to wrap their heads around it. It just seems like there's so much stuff out there. It seems unimaginable to think that we are alone in the universe. But as Arthur C. Clarke put it, either we are alone or we're not. And neither of those outcomes are particularly pleasant to think about. I think he phrased it, either we are alone or we are not, and both are equally terrifying. So I'd like to point out the fact that the fastest thing in the universe is still painfully slow. And it's currently the only thing besides politics that is holding us back from becoming a galactic civilization. So the International Space Station, it typically takes several hours to get into orbit and dock with the space station. But if you were a photon traveling at the speed of light, you would be able to do the whole thing in around 1/30th of a millisecond. The Apollo program, from John F. Kennedy's speech to the actual landing of Apollo 11, took just short of 7 years. But if you were a photon, you'd be able to do the entire program in 1.3 seconds. You'd be able to do the Mars program in 3 minutes. And beyond that, the distances start to get a little bit larger. Proxima Centauri B, the closest exoplanet beyond the solar system to us, is 4.1 light years away, which means it takes light 4.1 years to go from here to there. This is where the timeline gets a little strange, because if you look at Proxima Centauri B, you're seeing it as it was 4.1 years in the past. And if you if somebody happens to be on Proxima Centauri B studying the Earth for their PhD or something, they actually wouldn't know that there was a pandemic happening here, because light from Earth during the pandemic has not yet reached the closest planet to us. It will sometime next year. The Andromeda Galaxy, which is 2,500,000 light years away, gets even more freaky, because humanity has not existed for 2,500,000 years. Our primates were roaming the planet back then. So if people are studying Earth in the Andromeda Galaxy for their PhD, they do not yet know about us, and they will not for millions of years. There could be civilizations in the Andromeda Galaxy that have arisen and possibly gone quite far, but we may not even know about them yet because their light has not yet reached us. In fact, human civilization as we know it has not yet existed for even 100 millennia. So our light has not yet reached the other end of our own galaxy. The other end of the Milky Way is fundamentally unaware of our existence. How's that for a bit of cosmic perspective? So the largest thing we've ever discovered in the universe is an ultramassive black hole. They decided they needed a new category for black holes because supermassive wasn't enough. Ultramassive black holes weighing about as much as an entire galaxy of stars. It's around 30 times more massive than the entire solar system. And we were able to detect it from almost 20 billion light years away. You can literally see this thing through your telescope from a quarter of the way to the edge of the observable universe. It is freaky how powerful this thing is. The sun will emit a tremendous amount of energy from its birth to its death, 10 billion years. Yet that entire energy is emitted by this thing every, I believe it's 45 minutes. Every 45 minutes, this thing emits the amount of energy our sun will emit over its entire lifespan. So it is just, let's just not think about that, actually. It's incomprehensible. So one of the other things I like to do to put the universe in perspective is to point out that we totally made up the terms up and down. We seemed to think that the Earth's axis defined what was up and what was down. But one of the things I like to do is a little bit of a cosmic orientation to put our orientation and motion in perspective. I presume most of you are not moving very fast right now. Some of you, probably most of you, are sitting down while watching this. But in fact, you're moving at 300 meters per second, and relative to the Earth's axis, we're tilted at 41 degrees. In addition to that, the Earth is orbiting the sun at 23 degrees from its axial tilt and is moving at 30 kilometers a second, which means we are covering the length of Vancouver Island every 15 seconds in our motion around the sun. It gets a little more out of whack when you consider that the sun is moving around the Milky Way tilted at 60 degrees, and we are moving at 200 kilometers a second around the Milky Way, which is fast enough to cross the length of Vancouver Island in 2 seconds. And then just to finish things off, we like to orient our galaxies relative to the supergalactic plane, and the Milky Way is tilted 90 degrees from the supergalactic plane. And we're moving at 600 kilometers a second, which means we move the entire length of Vancouver Island in under a second. So bringing this back down to Earth, one of the things I like is when people say that they're going back to visit the place where, say, they got married, or to visit the place where they were born. And I'm like, no, you're not. No, that place is billions of kilometers away by this point. Your path through space kind of looks like this, and you are never, ever going to visit the same place twice. When I started this presentation, I was several million kilometers away from where I am right now, and so are you. And even if you're lying on the couch, you are moving at hypersonic velocities. In fact, you've moved more than the entire width of the Earth since this presentation started. So yeah, we're going pretty fast. So Carl Sagan said the famous phrase, "We are made of star stuff," and people have kind of accepted that as like the motto of astronomy. It almost seems a bit cliche, but it is true in every way of the words. Like, you think about it, we are literally made of star stuff, and I'd like to go a little more into detail about that. Anyone, if you've ever had to explain to people how babies are born, this is the extended timeline for how babies are made. So it starts like this. A supergiant star exists and it forms iron in its core, which can no longer sustain the fusion reaction. So the massive star collapses, forms a supernova, and in that supernova, it gets so hot that it fuses all the elements right up to 118. So only iron can be formed in regular stars. But in supernovas, you get all the heavy metals like tungsten, lead, gold, silver, and most of the stuff around us. So anything that is not below iron around you has to have started its existence in a supernova explosion and has just been cycled through and through and through processes. But really, the atoms around you started their existence at the heart of a collapsing star. And of course, all those guts got, all those stars' guts got strewn throughout space and came together in a fleeting form that we like to call you. So you are just a temporary arrangement of star stuff that will go back to the rest of the universe in the end. And I personally think that's very cool that we are the stuff of the universe capable of appreciating the universe. Speaking about the universe, as I have been this whole time, space and time are really weird. And we really started to get to know that in the early 1900s when Einstein derived his theory of relativity. So if you travel at near the speed of light, you might think that it would be the velocity that killed you, but it might just be the psychedelic experience that got you first. If you travel at near the speed of light, your whole perception of reality starts to come apart. And that's what I really love about the nature of the universe is I don't know if we will ever fully understand how weird reality is. So just notably, if you travel at near the speed of light, your vision becomes a fisheye lens because photons from behind your head start to come into your eyes from the side because you're practically moving right alongside them. Time slows down drastically, so people will see you in slow motion, but if you look back at them, you'll see them sped up like a time lapse. Due to the angles at which photons bounce off of you at near the speed of light, you get this weird Terrell effect where you can see the front, back, top, bottom, left, and right of an object all at once. If you look in front of you, photons are blue shifted and look bright blue. And if you look behind you, everything's a dim red. It's like the Doppler shift of sound, but with light. So instead of changing pitch, it changes color. You become a lot more massive. So if you're going on a diet, I wouldn't recommend traveling at near the speed of light. Since E equals mc squared, you become a lot more massive. And perhaps the wackiest of all, you become a pancake due to length contraction. And everything just happens from your point of view, but from others' point of view, you look weird. From your point of view, you look normal and everyone else looks weird. This is the nature of relative frames of reference, which is basically that everything is just relative to certain points of view and everything works fine, no matter what point of view you have. So if you cut a cake, you could keep the slice stationary and move the entire universe downward to serve your cake, but I wouldn't recommend that. It still works fine with physics. So this is one of the weird paradoxes of relativity, which is if a spaceship, such as the USS Enterprise, is traveling near the speed of light, if you're watching it, it is squished and the universe looks normal, but from its point of view, it looks normal and the universe is squished. These are both valid points of view, but in this case, the spaceship is shorter than the planet, and in this case, the planet is shorter than the spaceship. How does that work? Because we seemingly have a disagreement of perspectives. And this gives way to perhaps the weirdest paradox in all of space and the universe, which is the latter paradox, which is that if you happen to fly through your shed at near the speed of light, I don't know why you'd ever do that, but and you are trying to fit your ladder in the shed, you travel at near the speed of light, you become a pancake. So if someone's watching you, you can fit the ladder in just fine. But from your point of view, the shed is coming at you at near the speed of light. So the shed is a pancake. So you will not be able to fit your ladder in the shed. And the reason for this weird seeming paradox is that as you get to the speed of light, even the order that the events take place in stops working. So you cannot even agree which side of the ladder enters the shed first and which side of the ladder the shed exits first and last, and you literally cannot even agree on the order of events anymore. And by that point, well, you've basically lost all connection with a stationary reference point. And I hope this just gives you a sense of how weird space can get in the extremes. So the universe is a weird, weird place. This leads me to my next postulate, which is ever since we developed computers, people have wondered whether reality is just a simulation by some advanced civilization. And this isn't really a testable hypothesis. So I'd just like to brief over this. Some have suggested that the speed of light is kind of like the lag in a video game, but that's more speculation than fact. However, a mathematical experiment called Conway's Game of Life attempted to prove that it's possible to simulate living beings just using a simple set of computational rules. If it turns out to be true, you will be able to cheat on every test you will ever take, because that means it's possible to simulate the entire universe. Unfortunately, this is a long time in the making, and plenty of progress has been made. I meant to say no evidence has come of it yet that it's possible to simulate thinking minds. So far, the simulation hypothesis remains a hypothesis. We're ready to move on to more mind-boggling topics about the universe. Some have suggested that space is curved in the fourth dimension, which means that we would be living on the three-dimensional surface of a four-dimensional shape. Picture it like a sheet of paper. So if you have two-dimensional creatures living on a flat three-dimensional sheet of paper, they think they're living in a flat two-dimensional universe. If you bend it in the third dimension, they will still see a two-dimensional space because they will be bent right along with it, which means we could be bent in the fourth dimension right along with our three-dimensional space. And there are several possible shapes for the universe. Could be a four-dimensional sphere called a hypersphere, a four-dimensional saddle, or a flat three-dimensional plane floating in four-dimensional space. There isn't any way to see the difference because everything just looks like normal three-dimensional space. But if you shine two laser beams, and this is an interesting way of testing it, in flat three-dimensional space, you'd expect those two laser beams to just keep going straight forever. Two parallel lines will never meet. However, if the universe is curved in the fourth dimension, even parallel lines will either converge, bend toward each other, or bend away from each other. As you can see in this sphere diagram, if the universe is a hypersphere, two seemingly straight lines will eventually converge and intersect, and will even travel around the entire universe right back to where they started, which means if you look up in the sky one day and you see a copy of Earth in the distance, well, that's proof right about there that we are living on the three-dimensional surface of a four-dimensional hypersphere. However, this is one of those things that we may be able to solve in the future, but so far, the curvature of space remains shrouded in mystery. One of my favorite facts, mind-blowing facts about the universe is that matter contains positive energy and gravitational attraction has negative energy. And in fact, when you add it all up, the amount of matter energy, or the amount of mass energy in the universe exactly cancels out the amount of gravitational energy in the universe, which means the amount of mass energy in the universe is zero, which means that the universe is just an iteration of nothing. And we ultimately add up to nothing, which is like the perfect defense for a nihilistic universe. So no matter how much value you ascribe to something, it is literally, it adds up to zero in the end. So that's one of my favorite facts about the universe. So when you get down to the absolute, there are only four possibilities for what the universe really is. So the universe either is finite in distance, so it has an edge, or it is infinite in distance, as in it goes on forever, and it is either finite in time, as in it will have an end, or it is infinite in time, as in it will go on forever. And in my opinion, no matter what this turns out to be true, there are mind-blowing facts in store. So no matter what the universe turns out to be, it's going to be mind-blowing anyway. So if the universe has an edge and it will ultimately end in some way, the question immediately becomes, well, what is beyond the edge? What will happen after the universe ends? Our minds are not really geared to contemplate non-existence. So the question ultimately arises, if there's an edge, what's past the edge? Is it nothingness? But then immediately it becomes, well, that's just empty space, and space exists. So if you know what's beyond the edge, I'm happy to say there's a Nobel Prize waiting for you. So feel free to post that in the chat. If you know what's beyond the edge of the universe, I'd be happy to chat with you later about that. And like I said, the universe could be finite, but still go on forever. Like I said, if the universe is a sphere, you can go on forever and just loop back on yourself over and over and over again, but the universe is still contained in a finite space. Perhaps my favorite universe possibility is that we live in an infinite universe that goes on forever. And this is where the weird nature of infinity comes in, which is that anything with a non-zero probability of happening is guaranteed to happen, and it is happening somewhere right now, and it is happening an infinite amount of times, which means everything you could possibly imagine and everything you could possibly not imagine, everything you are doing right now, everything you will ever do, everything you won't ever do, every experience you will and won't ever have, it's happening right now an infinite amount of times. There are an infinite amount of versions of this where I'm giving this presentation, and right about now I get vaporized by a Death Star by the Galactic Empire. Personally, it's an interesting thought because there are copies of you out there. There are 10 to the power of 10 to the power of 70 possible ways to arrange all your particles, which is a tremendous number, but it's not infinite, which means if the universe is infinite in size, eventually it has to use up all those possible arrangements. So there have to be copies of you out there doing either the same things that you're doing right now or different things, things that you may not want yourself to be doing right now. But who am I to say? It's infinity. And the other infinite possibility is that the universe continues forever. It may not be infinite in size, but it might exist forever. And given our current understanding of the universe, things are going to get bleak extremely quickly on the cosmic scale. Blink of an eye, the sun is gone, the earth is destroyed. That happens in a mere 5 billion years from now. And in a mere trillion years from now, all the stars are dead. In a quadrillion years from now, the remnants of all those stars begin to cool off into black dwarfs, which are essentially cooled off remnants of once glorious stars. Again, this is just a blink of an eye in the story of the universe. And around this time, too, the galaxies will fly apart just due to random gravitational interactions pulling them apart. In around a decillion years from now, that's a 1 with 33 zeros, it is hypothesized that protons themselves, the very particles that make us up, will break down into nothingness. So if there are still people around, they will have to deal with their bodies falling apart, which will probably be pretty awkward. And beyond that, even the black holes will fall apart, evaporating away to nothingness due to a weird aspect where mass actually escapes from black holes due to Hawking radiation, and they'll just get smaller and smaller and smaller until they explode in a giant explosion. If protons don't decay, everything will decay into iron, and that iron will stay there for practically forever in weird clumps called iron stars until they suddenly explode in around 10 to the power of 32,000 years from now, which is so long, it's okay to call it forever. Mathematicians won't get mad at you. However, even beyond that, even beyond the true darkness, even beyond these final fireworks in the universe, there won't be nothing because space itself has these weird quantum fluctuations, which are particles and antiparticles that are just appearing and disappearing all the time. And the weird thing is, if you wait long enough, you'll get these random combinations of particles appearing in just the right way for structures and weird objects to suddenly appear and then disappear. So if you wait long enough, you get, say, a piano. A piano just appears in space and then it disappears. And this is one of the weird aspects of the universe in that the quantum realm is all about probability. So if you wait long enough, you should get an entire universe just appearing. Just imagine, like, there's nothing and then there's an entire universe. And this is one of the theories for the Big Bang, which is that the Big Bang was just a quantum fluctuation. It was just a huge explosion of particles that just appeared out of seemingly nothingness. There are around 10 to the power of 10 to the power of 115 ways you can arrange the universe. And eventually, you should get all these possible combinations, which means, given enough time, you should randomly get an exact copy of this universe just appearing due to quantum fluctuations. And that would take around 10 to the power of 10 to the power of 10 to the power of 56 years to take place. And I'm not even going to begin to describe how huge this number is. But if this theory turns out to be true, and it's called the Poincaré recurrence, it means that eventually, just by random chance, there will be an exact replica of this universe in an unimaginable amount of time from now, with exact copies of us, exactly where we are right now, watching this exact presentation on our exact devices, with an exact replica of me talking about exact replicas of us watching this presentation in the future. If that sounds a little bit mind-boggling, this last bit gets a little bit worse. This is fit to give you the roughest existential crisis you'll ever have. And it is probably the weirdest aspect of the quantum nature of the universe, which is that if you can get whole universes appearing out of the vacuum of space, it seems a little bit more likely that you'd get something less complicated than a whole universe, like a single galaxy. Or, you know, not even a galaxy, maybe just a solar system, or maybe just a planet appearing, or maybe just a person appearing, or maybe just a human brain. And it would only take around 10 to the power of 10 to the power of 50 years for a Boltzmann brain. That's what these weird hypothetical brains are called, compared to 10 to the power of 10 to the power of 10 to the power of 56 years. It is so much more likely for a single human brain to appear than an entire universe that it's raised this really disturbing question, which is, statistically, wouldn't it be more likely for you to just be one of these disembodied quantum-formed brains imagining that it's living out this existence in an imaginary universe, watching an imaginary presentation done by an imaginary person named Nathan Hellner-Mestelman? And with that, I think I would like to bring it down to earth again. Oh, by the way, this is impossible to test, but given that you've made it through this lecture, we can probably say that you're not one of these Boltzmann brains, because given that these brains are formed out of the vacuum of space, they would almost immediately phase out of existence again. And given that you watched this entire presentation successfully without phasing out of existence, we can probably say you are not a quantum-formed disembodied human brain. So to bring this back down to earth, I'd just like to end on an optimistic note. The joy of not knowing is so awesome, in my opinion. It really puts us in perspective. And I'd like to raise a few points just so you can go away from this presentation afterwards and feel like important in this universe. I think that we are tremendously lucky to exist in the first place. But just some awesome notes to take with you. The human brain is literally a kilogram-sized loaf of meat, but we are somehow able to comprehend this awesome, vast universe that is so much bigger than us. Like I said, it was something like 10 to the power of 76 times bigger than a human brain, and yet we're able to comprehend it. And if you're passionate about space, you're the matter of the universe appreciating itself. That's a pretty nice fact to know. And as Arthur C. Clarke puts it, if we are alone in the universe, it's terrifying. But if we are alone in the universe, then by existing, you're carrying the torch of life forward. And you are the universe appreciating itself. And as Carl Sagan said, you're made of star stuff. So you might think you are separate from the universe, but really we are not studying the universe. We are the universe. And with that, that is my presentation. Thank you so much for having me. And I'm happy to take any questions you might have about this big, awesome, wonderful universe we live in.
Yeah, thank you, Nathan. Yeah, that's what we can do next. If anybody does have any questions, we'll just wait. If there are, you're welcome to chime in, anybody.
I have a question, Nathan.
Yeah.
You quote a lot of numbers in this presentation. Where do the numbers come from?
Oh, well, that comes from a branch of it's statistical mechanics, which is basically, or especially the numbers about like probabilities, which is just the probability that you'll find particles in any one specific state. That, of course, is random. So a whole universe might appear right now outside my window, but it's very unlikely that that would happen. And then the numbers about how many galaxies are behind your thumb, that's just taking the angular area of your thumb against the sky and dividing the total number of galaxies in the universe by the area of your thumb. And that way you get the number of galaxies that your thumb is covering every time you hold your thumb up, which is absolutely mind-boggling. So yeah, that's what I love about math, is that it can be used to solve real-world problems, but it can also be used to solve ridiculous hypothetical things that just, it's like a playground for your mind. That's what I like about that.
Yeah, I think you have to get used to the concept of truly not being exact.
Yeah.
in a lot of ways. Great, thank you.
And Lori, you have a question?
Yeah. Hi, thanks, Nathan. This is awesome. I mean, it is totally mind-boggling. I'm wondering how you might fit some of the indigenous ways of learning, the indigenous ways of knowing, into some of this. I don't know whether you've had a chance to do any of that. Is there a lot of the two-eyed seeing, and that we need to look at different ways of knowing? Like, I think you kind of hit on quite a bit of that, but have you done any work on that at all?
I haven't really been involved that much in that, but their way of learning and knowledge is so fascinating to me. That's part of it really does change the way you look at things. And I think in connection to the way we can see ourselves amidst the universe, I think there is a connection there. Like, it does seem kind of like that way of thinking.
Yeah. Well, there's just too many things here on Earth that are amazing, that we are looking at ourselves as this, this centric group of things that seem to be, better than everybody else, but in fact, actually, we're all just completely connected. So
yeah, we are just a byproduct of the universe.
Yeah.
Okay, that might be it. I don't see any other questions like in chat or anything. So I'd like to thank you again, Nathan. That was really brilliant and a lot of fun to explore those big but also silly questions. So the next thing we have going on is the EAA. So I'll have David Lee come on, and I'll let you take it away.
Great, thank you, Calvin, and thank you, Nathan. And Nathan, if you could stick around, there's you're part of the community that witnessed the Mars occultation. So I want you to stick around, because you might have to explain a few things.
Sure. Okay.
So so tonight we've got some reportage of the Mars occultation. I mean, the thing that many of us were waiting for in December was the opposition of Mars, and also the possibility of seeing this occultation. Now, as we all know, Victoria cooperated by providing us with clouds and rain. And but I also want to say, as astronomy enthusiasts, as Nathan says, we don't tend to give up. We'll come out to the party anyways, whether we think it's going to be a good time or not. So this is a story about that. So just let me share my screen. Also, we will have possibly some images from Dan from the Plaskett, possibly. So after this little thing about Mars, we'll talk about that. So yeah, there was a couple of things. We basically were waiting for this moment, and Bill Weir, who is actually one of the people in our community that actually visually observes and sketches. You'll see the reason why I'm introducing this in the electronic imaging portion of this show, because you'll see there's a punchline at the end. So yeah, so the lunar occultation of Mars, you can see the drippy cloud there. Bill has been sort of observing and sketching Mars all along for the last couple of months, and this one is actually quite a recent sketch from the 15th. All of us have been basically observing and imaging through holes in the sky. So Brock, actually, and you can chime in on this one as well, Brock. You started early. This is from the beginning of October, I think.
Yeah, that at that time of the year, Mars wasn't really visible in the early evening, so I was just catching it early in the morning. So I think it was 5 in the morning or something like that. And of course, at that time, it was quite a bit before the opposition. So you can see it's partially illuminated.
Right. So on the day of the occultation, I think most of us had given up. Like we were all watching, I think Griffith Observatory or something. We're watching broadcasts from other areas. But I mean, I went out anyways. I kind of always am curious. I always end up with photographs of clouds, which is a part of my signature, I guess. You can actually see Mars. This is Mars approaching the moon. You can see it right there. I was expecting better, actually. You know, like I remember sort of conversing on email, saying that I had seen the moon and it looks pretty clear, but it went from okay to not so good. But many of us were out there watching, many of us visually, and some of us imaging. But you can tell that really it was pretty miserable out. So Brian Barber was out as well with his Dob, and you can see he was able to sort of catch Mars approaching and also touching. I actually missed this part. Where I am, where I live, I couldn't actually see that. So the cloud cover actually varies even within the city. And Nathan, is this the exit? Nathan, are you there?
Yeah. That was actually the first contact.
Okay. So it's just the orientation then. I wasn't quite sure.
It was too cloudy to spot the lunar details for orientation anyway. So
do you want to comment a little bit about your experience? What was happening?
Sure. Yeah, it happened way faster than I thought. Actually, the whole approach was pretty slow, but when it actually contacted, I suppose that's a very geocentric perspective, but when it passed in front of Mars, the whole thing took like 15 seconds, maybe 20 seconds.
Oh, okay.
It really made me appreciate how the moon really is moving around the Earth. Like, I mean, people innately know that, but that was probably the first time I saw that directly. So quite a cool cosmic perspective.
Yeah, I've always enjoyed planetary transits and occultations as well for the same reason, right? Because it does definitely give you that perspective. And I'll have to say, I think the visual people probably won during this occultation because most of the shots were pretty miserable. But I actually still remember the view through my refractor. It was actually the best of the things that I did that evening. So Brock, you sent a note recently saying that you managed to get this. So this is very recent.
Yeah, this is just a couple of days ago.
Just a couple of days ago.
Yeah.
And did you have to wait for an opening, or did you have like a lot of hours to do this?
No, I was waiting for openings. I was out there freezing and waiting for the clouds to go by, and then be a little bit. And then most of the shots I had, it was bright, and it was getting brighter and dimmer because the clouds were, it looked almost clear, but you could tell by the video that it wasn't. It was, the brightness of Mars was changing dramatically. So, but I did get a couple really clear openings, and that's when I managed to get a little bit.
Yeah,
So Brock,
Okay.
is this just a one little part of that video then? You just kind of chose the best, or is it the lucky imaging?
It's lucky imaging. So
Okay.
there's
We'll actually try to talk very briefly
okay.
about that in a minute or two, actually.
Mhm.
Yeah. So in order to get this, I mean, the distance shots are a piece of cake because you're not looking for any detail there. If you got a disk of Mars, you're happy, right? But Brock is really kind of just zooming in on this, like we're using quite a long focal length when we see these planetary images. So I thought I would take now at the beginning of the presentation, we had a sketch that Bill Weir did, and I'm pretty sure they only differ by about a day, I think, because I'm pretty sure Bill dated this as the 15th of December, and Brock, this would have been the 16th for you. Perhaps
was it 16th? I think it was might have been the 15th actually.
Oh, 15th. So this probably pretty close then, right?
Mm-hmm.
So I had to flip Bill's sketch around to match the orientation that Brock has for the image, but yeah, you can actually see the features. It was quite interesting how well Bill's eye is in sort of determining the details in the image. So just to talk about the technique that Brock used and maybe to infer what Bill was doing. Bill was actually just observing through a telescope and drawing what he could discern. Now, I don't know whether we would be like a computer and doing what Brock will describe to you, but in our own mind, I guess we do, in a sense, cull and integrate the imagery that we see with our eyes. So I'm assuming as an experienced observer, that's what Bill's doing here. So Brock's result is the result of something else. So we're basically using something called lucky imaging. I'm going to leave the screen here, Brock, if you want to show the raw results of what you were working from.
So this, if you can see it, is actual raw video that I used for that image. And you can see the seeing wasn't spectacularly good. It was actually wobbling around quite a bit. But that image is basically a creation from, there's about, in this video, there are over 10,000 frames, which are 10,000 individual pictures. And there's a couple of different software packages that allow you to analyze all 10,000 frames and pick the very best. And then you take the very best and you stack them together and create the final image. And so this would have been about, I think, 15 or 20% of the 10,000. So somewhere in the maybe 2,000 images that were actually used in that final image and basically stacked on top of each other to essentially generate that final image.
Yeah, I can actually see the hints of the structure.
Yeah,
but obviously the processing involves probably the enhancement of edges as well.
Yes, there's edge enhancement, and there's a methodology called wavelet sharpening, which basically uses Fourier transforms and helps to filter out the different frequencies in the image and can help to really bring out detail. But if you're watching it, you will see the odd little glimpse, and you see the same if you do a lot of visual astronomy, looking through eyepieces, you'll see the same. And that's what Bill's seeing. It'll look like nothing, and then you'll just get that little glimpse of just brilliant clarity, and then you'll remember that and you'll sketch that. And that's essentially what I think Bill is in a sense doing something very similar, but just using his mind and his eyes. Because when you're visually observing, you'll have the same thing where it'll look, you won't be able to see detail, and then you'll get that little momentary flash of just perfect clarity. And that's what you remember, and you make the little sketch. And the computer's doing the same thing where you have 10,000 frames, and every once in a while there's just that moment of clarity. It might not even be in the entire disk. It might just be one portion of the planet is momentarily just super clear, and that little bit of clear is added to another little bit of clear, and eventually it all stacks up to give you much, much better.
Yes. Yeah, for sure. Does that answer your question, Lori? Oh, I can't hear you.
Yeah, I was just saying, it's just beautiful. Yeah, it's amazing. Yeah, thank you.
Right. So, Dan, are you online?
I am, and I'll quickly grab the
You
screen
wanna
here.
you wanna
So
take the
just
screen?
Give me a sec. Just gonna pop screen. Okay, so one thing that came up during Nathan's talk was that it reminded me that the questions of the scale of the universe are not a new one. And so I went digging while he was chatting, and pulled up an excerpt table from one of Plaskett's articles discussing the scale and size of the universe. And this is the first example of a proper scale going all the way from, in this case, electron. So I don't know whether the Planck length was in vogue at this point or not, up to, at that point, the Einsteinian universe. And when you think that the great debate in astronomy, the whole concept of whether the spiral nebula were indeed other island universes or whether they were part of our own galaxy and were just stars being formed, was only settled in 1925 by Hubble and was still raging strong for the centuries before that. And certainly, I think it was 1921, the actual so-called Great Debate took place. To have a number like 170 billion light years as the scope and scale of the universe that had previously, just a decade and a half before, been limited to about 100,000 to 300,000 light years, depending on who you talk to, is staggering to think about. So I just thought I'd pull that one out, because it's it's not a new thing to be thinking about all this. And if you want to twist your head in the other direction and go for the quantum, the usual figure given is that the nucleus of a atom is, a marble inside a baseball stadium, as your typical kind of scale. And so all these comfy chairs that we're sitting in as we're getting catapulted around the universe, there's at least a chance that you could just fall right through it at any given moment because of all that clear space. It's the forces that are keeping you up, not anything that's actually there. So it's kind of the opposite of galaxies colliding, which is that the odds of stars hitting each other are very low. But in this case, the odds of, and let me get that out of here, the odds of us not going through the door are very low. Just one sec. I can't see my own images to do this. Okay. I'll get you over here. There we go. So, talking about galaxies colliding, one of the images I was able to capture with the Plaskett this fall was Stephan's quintet. And this one was recently in the news over the summer, being one of the first images taken with the Webb telescope. What a fantastic shot. And so I figured, given we had some time on the Plaskett in the fall, it would be nice to turn to it and look at this cluster or interacting grouping of galaxies. So the quintet are these five that you can see right here. But this big blue galaxy, I think it's NGC 7320, has been shown to only be about 40 or so million light years away, rather than the approximately 300 million that the rest of these are. And so it's not part of the group, but it still forms the visual quintuplet that you get for Stephan's quintet. And what you're seeing in the background are these very different shapes of the galaxies, because they've been colliding, they've been interacting. These two are in the midst of an interaction. Both these bright blobs are the nuclei of main galaxies. And so you're seeing the stars ripped out into these lovely tidal streamers. And you're also seeing the effect of gravitational redshift, which Nathan started to get into a little bit as well, which is that light doesn't behave the way that you would necessarily expect the farther out you go. And so because these galaxies are moving away faster and farther from us, and they're in gravity wells, you get these interesting shifts in the wavelength of light where they appear this more kind of dull, orangey yellow rather than the bright blue of the galaxy in front. If you brought these all forward to be at about 40 or so million light years, they would all look more or less blue, like this one over here. Why the arms appear blue is that apparently hitting things creates some kind of inspiration, because there's a lot of star formation that goes on when you get galaxies interacting that gets caught up in these arms as the gas gets churned up and new stars start to form. A couple other ones, and I'm going to be quick because I know it's the end of the night for everybody. Just to cycle through some shots from the Plaskett. We took some data in the summer on the elephant's trunk, and then I colorized it with data that I captured from some much smaller telescopes, but it really gave a better look at what the Plaskett was doing with that big ability to grasp light. This is very deep for a target like this in natural light. We also shot the Great Cluster in Hercules, which is a globular cluster, give or take 30,000 light years away. If you're interested in some nighttime reading, take a look at this one and look up the Arecibo message. And then thinking of Nathan's talk, whether or not that message would have ever arrived, because there's a bit of a problem even if you're pointing light at something, it goes very fast, but it takes a while to get there and things don't like to move. We also shot a couple planetary nebula. To twist your mind in a different way, this is the fate of our own solar system. So when the sun eventually dies, our skies will look glorious, but we won't be around to see them. And so what you're seeing is the material from a dying star that's pushed out into a shell. This is a false color image because I couldn't make the frames play nicely coming out of the Plaskett. So I just decided to go with contrast and appearance over an actual representation of color. Same thing here. Another planetary nebula. This one, the data was a bit more difficult to fight with, but I tried to do my best to show that there are different shock waves of color and therefore different elements at work within the different filters in the planetary nebula. I processed this up while we were in the midst of the talk, but I just was looking through my old data catalogs and seeing if I could find something. This is a glimpse into the Cygnus wall with the Plaskett. And what's interesting about it is that you can see a lot of the same features that the Plaskett can with an amateur telescope. And so I pulled up my amateur telescope image that I took of this in the summer. But the level of detail that you capture with the Plaskett is just in an entire different realm. If you look at how nice and nuanced all of these features are through here in something like 10 minutes versus the 12 hours that other frame was, it's on an entire different staggering scale. Thought that everybody might be a little bit interested in that comparison. And then finally, we have the Cocoon Nebula, which is about the closest I've been able to get to natural color out of the Sloan Digital Sky Survey photometric filters that we're using. But this is a neat blend of an emission nebula, a little bit of reflection, and some darky nebula, all playing nicely in the same space, so that you get kind of the three different main types of nebula all on the same image, and it looks pretty. Any questions on any of those?
Yeah, thanks for that, Dan. Yeah, it's awesome to see these Plaskett images. I wanted to know, so you just had these sort of in your pocket, you've taken these, I guess the dates up there.
I took them over two nights. So these were, I think, taken July 29th or July 30th in the summer, and September something, late September this fall. All my other nights have been rained out. I do have a night on the 22nd, which I was really looking forward to because Back in the 1920s, there was a competition on who could operate for the longest night of the year, and the astronomers used to fight each other for who could take the most slides. And you have to understand, it was much more complex back then to take a frame. I mean, all of these images are made up of usually dozens of separate individual frames. But back then, you had to do it all on one piece of photographic plate. And so I think the record was somewhere in the 70s or 80s for the most plates taken in a night, and the longest night worked was something like 14 hours. And so if it were clear on the 22nd instead of snowing, as the forecast currently shows, I would have been able to get into the parking lot at about 3 in the afternoon. Then you would take your calibration and flat frames to get set up for the evening. After you've done that, you would get the equivalent of the month of June in your night. And then you would roll out of there somewhere at around 8:30 in the morning after you finish taking the rest of your calibration frames. So astronomers at this latitude have a bit of a duplicitous existence, where in the summer they get off a little bit easy when they only really have 1 hour of darkness. So maybe there's 5 hours of work or so that you get tied up with the observational pieces, and the rest of it's actually getting to move through your work. In the winter, it's the opposite, where the observational time is limited, but if you get a clear night, you can do more work in one of these winter nights than you can do as I wasn't actually really lying. It probably would outweigh the amount of good data you could take for the entire month of June. So unfortunately not this year, but I was quite excited about it.
Yeah, that's brilliant.
Well, that's great. I just wanted to say, what a great summer we had. Like we really, I've never seen that many clear nights. So it was very, very good. So I think if things are not so good at the end of the year, we probably have nothing to complain about.
We definitely don't. It's been a good run, and hopefully we have another good summer of good weather without too much smoke to welcome everybody back onto the hill in the spring and into next summer. And so I guess that's it for me. So Happy New Year, everybody. I'll turn it back over to you.
Yeah. Well, yeah, we're going to wind it down anyway. So yeah, thanks, guys. Excellent always hearing from the EAA team. And that's it for us for Saturday night star parties for the year. And I guess we will see you all in the new year. So good night, everybody.
Good night.
That's if we don't phase out of existence. Good night.